Tired of slow LLMs devouring your memory? Frustrated running them locally? In this video, we will go through the revolutionary technology that makes lightning fast AI possible on your M1 laptop. No more waiting. Pure AI at your fingertips. Hi, my name is Jaideep. I have 14 years of experience working with top companies in AI, and in this channel, I talk about Gen AI career in the industry. Please like this video and subscribe to the channel. So before we start, we will go through a little bit of the background first. So this is the CPU and the GPU architectures. A CPU consists of few cores optimized for general purpose sequential and serial processing. CPUs are designed to complete tasks with the lowest possible latency and can quickly switch between operations. There is a PCI bus, system agent, memory controller, and DDR memory. There is the L3 cache for all the cores. L2 supports individual cores. Separate L1 data cache for data and instructions. If data isn't found in the cache layers, the CPU retrieves it from the main memory, prioritizing low latency access for efficiency. In GPUs, there are massive number of cores. For example, the latest H100 series from NVIDIA has 16,896 cores. Since there are so many cores, there are processor clusters of streaming multiprocessors. Each SM typically has an L1 cache for quick access to instructions. The SMs utilize a shared L2 cache before accessing high-speed memory. Unlike CPUs, GPUs are designed to tolerate higher memory latency. They dedicate more transistors to computation rather than caching. The architecture focuses on keeping the CPU busy with parallel computations despite slower memory access. So the difference is that CPUs are optimized for low latency sequential processing. GPUs are optimized for high throughput parallel processing. So the result is that GPU operations become faster if there is less transfer of data and more focus on computation. One of the ways to make LLMs faster is through quantization. As you know, the weights in the LLMs as well as the input data is converted to tensors. On a side note, check out my recent video on DeepSeek. They have used some nice quantization there. With quantization, you convert a model weights and activations from higher precision to lower precision. Quantization makes inference faster because reducing precision speeds up inference time because it requires less memory. Less bandwidth is required for transfer of data and less time for calculations. Traditionally, the preferred precision that was utilized was either floating point 32 or floating point 16. Generally, this data is converted to from FP16 to int8. Even int4 quantization has been quite successful, and now efforts are being made so that int2 is being explored. There are many ways you can perform quantization. A simple way to do quantization is to just reduce the precision of the weights in the model. This is also called the round to nearest or the RTN approach. Rounding by itself is a rabbit hole. Ideal characteristics of the rounding method include rounding should be done by a function. This way, when the same input is rounded in different instances, the output is unchanged. Calculations done with rounding should be close to those without rounding. To be considered rounding, the range will be a subset of the domain. So in that way, this is different from quantization, where the numbers may change. Rounding should preserve symmetries that already exist between the domain and the range. With finite precision, this translates to removing bias. A rounding method should have utility in computer science or human arithmetic, where finite precision is used and speed is a consideration. By default, if you create a random matrix in Torch, it will create the float values in float 32 precision. A floating point variable can represent a wider range of numbers than a fixed point variable of the same bit width at the cost of precision. As per Wikipedia, the range of floating values is 3.40 into 10 to the power 38, while that of integer bit is only 2 to the power 31, so, or rather 10 to the power 9 values. No matter whatever number you want to identify, in many cases you are quantizing in any case. For example, in case of irrational numbers, because of the inherent limitations of computer systems. And then there is additional loss of precision because you want to expand your range of numbers that you want to represent. So here you can understand that if you want to give form to knowledge, you are in any case bringing in some loss in information. So the question becomes, what is an acceptable loss of precision? And my ideal scenario would be, what is the accuracy on your domain and on your benchmark dataset? But if you're creating a general model, in which case there is probably not, in which case this is probably not there. But if you're creating a general model, maybe quantization error is fine. By the way, I have a video about LLM evaluation. Please have a look. Of course, if you are downcasting to float 16, the memory taken becomes half of before. So before it was 36, now it is 18. And then I can take a heat map of the various errors in the matrix. Here I have taken the absolute values and multiplied by 100,000. For deep learning applications, Google came up with this format called BrainFloat 16 or BFloat 16, which has the same number of bits as float 16, but the dynamic range is the same as a float 32 because exponent of BFloat 16 floating point is the same as float 32. As per available literature, training with BFloat 16 setting is more robust and is less prone to underflows, overflows, or any other numerical instability during training compared to training with pure float 32 D type. So in many ways, BFloat is really useful if you are doing training. Interestingly, similar to the errors we got from FP16 quantization, we check the quantization error for BFloat 16 as well. To compare, we take the sum of the absolute values of the errors. So I took 1000 random tensors and then took the distribution of the errors. If the matrix is small, then the BFloat 16 BF16 errors are more wide, but if we increase the size of the matrix, then the BF16 errors become more pronounced and separated out. Even though BF16 is not enough for today's quantization needs, at least I am able to load a decent LLM such as Llama 3 8 billion instruct model on Colab, which has around 16 GB GPU memory. The unquantized one was giving memory error and I was not able to load it. But using BF16, total around 12 GB is being used. The perplexity, testing for perplexity of the model, I am getting perplexity of 5.2 and total 10 minutes was taken for around 398 questions. So for that I had, so this is my calculate perplexity function. So for this I had taken 100 lines from this code text Python dataset. So using that, if we calculate the perplexity, it's coming up as 5.28. So now we go to the main research on quantization. There are two types of quantization. Model quantization, where you quantize based on analysis of the weights, and activation quantization, where you do the quantization of the activations. Above BF16 model is BF16 is model quantization because you are changing the weights of the model without thinking about how the performance would be. So a popular quantization for both is linear quantization. Within linear quantization, there is the 0 point quantization. The data camp has a nice explanation regarding this. Linear quantization is also called affine quantization. Is simple as shown in the formulas here. You, you scale the total range to fit as per the range of the quantized values. The 0 point is there to ensure that 0 in the floating range is accurately represented by an integer. This maintains numerical stability, especially for values close to 0. Then you quantize whatever values come. The rounding operation ensures that the final result is a discrete integer suitable for storage and computation in lower precision formats. During inference, you dequantize the values, and these are used for calculations to achieve higher precision, although only the quantized weights are stored. You can perform linear quantization on the models using the optimum quanto library from Hugging Face. So we downloaded the Llama 3.2 1 billion instruct. This has around 4 GB of memory and it's in TorchFloat 32. So these are some of the tensor values. So once we do the quantization using optimum quanto library into QInt8, actually the size has increased a little bit, but if you see the Q projection, K projection, all these have become the Q linear from linear. So here it was linear, and here after quantization they have become Q linear. So if you see the unquantized weights, that is after dequantization, it's very similar. So it's like 0.0259, 0.26. Here it is minus 0.123. Here it is minus 0.124. So they are very close to each other. If you print the weight, you'll see that the quantized values are a minus 1944.3, and these are the scale values. So you can do activation quantization as well, and not just weight quantization, which is basically quantizing the output of the neurons after performing the quantization. This type of quantization has essentially better promise on paper, but is more difficult to achieve. Unlike weights, which are static and constant once the model is trained, activations are dynamic. This means that activation change with each input to the network, making their range harder to predict. LLMs are notoriously difficult to quantize due to the outlier in the activations. In case of weights, the weight distribution is quite random, and hence they are easy to quantize. Outliers make activation quantization difficult. The scale of outliers in activations is around 100x larger than most of the activation values. In case of per tensor quantization, the large outliers dominate the maximum magnitude measurement and effective, leading to low effective quantization levels for non-outlier channels. And outliers persist in the fixed channels. Outliers appear in a small fraction of the channels. If one channel has an outlier, it persistently appears in all tokens. The variance among the channels for a given token is large, but the variance between the magnitudes of a given channel across tokens is small, so outlier channels are consistently large. Here is another visualization of the same observation. Outliers persist in the fixed channels. Outlier appears in a small fraction of the channels. If one channel has an outlier, it persistently appears in all tokens. The variance amongst the channels for a given token is large, but the variance between the magnitudes of a given channel across tokens is small. As per Quanto, you can do both weight and activation quantization, and if you are doing activation quantization, then you need to uh, calibrate the quantization as well using this calibration. But when running this, I was essentially having memory issue. But even if this code is not usable, if you see here, they are using activation quantization using the absolute maximum or the absmax algorithm. So the code is quite easy to understand. So the absmax algorithm will look something like this. Next important concept is block quantization. As we have discussed till now, the main problem with linear quantization is that outliers can have a disproportionate impact on scaling. The full range of the lower precision data type isn't used effectively, which lowers the quantized model's accuracy. The solution to this is quantizing in blocks, whereby weights are divided into groups of 64 or 128, for example, according to their value. Each block is then quantized individually to mitigate the effect of outliers and increase precision. Something to factor in, however, is that while an LLM's weights and activations will be quantized to reduce its size, they will be dequantized at inference time. So the necessary computations going forward and backward propagation can be performed with a higher precision data type. This means that the scaling factors for each block must also be stored. Consequently, this we have seen in linear quantization. Consequently, the more blocks that are used during the quantization process, the higher the accuracy, but the higher the number of scaling factors that must also be saved. So, more number of block quantization is like halfway between full quantization and not doing any quantization. The famous GGF quantization uses this block quantization to quantize the LLMs. GGF library uses block quantization. So the basic idea is that chunks of n elements each preceded with a block header which has some information to help dequantize more accurately. The simplest example is the Q8. It has a block size of 32 and each block consists of a float 16 data field and 32 int 8 quants. So the type struct is shown here. Most of the other quantizations are more complicated and may store some fields like minimum value, split of the data for easier processing, etc. The general idea of it being split into chunks with some information about the chunk content to assist accurately recovering the information holds for all of them, though. There are two forms of quantization of the activations is static quantization and dynamic quantization. The previous quantization that we discussed just now was an example of static quantization where we calculate the 0 point and scale prior to inference using a calibration dataset. So the steps for the dynamic quantization process. So let's consider hidden layer 1 and hidden layer 2. We forward pass through the hidden layer. We collect the layer activations and then we analyze the activation distribution. Once that is done, we calculate the quantization parameters 0.z and scale factor s. These values are then used to quantize for the layer specific parameters, the quantization parameters for the layer specific parameter. This process is repeated each time data passes through a new layer. Therefore, each layer has its own separate parameter values and therefore different quantization schemes. Dynamic quantization is relatively free of tuning parameters, which makes it well suited to be added into production pipelines. In general, dynamic quantization tends to be a little bit more accurate since it only attempts to calculate the Z and S values per hidden layer. However, it might increase compute time as these values need to be calculated. Now let's talk about QAT or Quantization Aware Training. Overall, there are two ways you can perform quantization. Post-training quantization, where we take an already trained model and perform quantization on it. The methods that we have discussed before are post-training quantization methods. Let's review post-quantization training shortly so that we can understand QAT better. Post-training quantization schemes quantize models in a greedy fashion. Specifically, these algorithms usually optimize an auxiliary loss function representing the distance between the quantized and the unquantized operands and parameters in the network. The operation is applied on a per layer basis using only a few training samples known as the calibration set. Although these approaches are computationally inexpensive, they often decrease network accuracy. There are various recipes to perform QAT, from starting with an untrained model to starting with a pre-trained model. All recipes change the training regimen to include the quantization error in the training loss by inserting fake quantization operations into the training graph to simulate the quantization of data and parameters. These operations are called fake because they quantize the data but then immediately dequantize the data, so the operations compute remain in the floating point precision. This trick adds quantization noise without changing much in the deep learning framework. In the forward pass, you fake quantize the floating point weights and activations and use these fake quantized weights and activations to perform the layer operations. In the backward pass, you use the weights gradients to update the floating point weights to deal with the quantization gradient, which is zero almost everywhere except for points which is undefined. You use the straight through estimator, which passes the gradient as is through the fake quantization operator. When the QAT process is done, the fake quantization layers hold the quantization scales that you use to quantize the weights and activations. Then the model is used for inference. The straight through estimator was given by the famous Yoshua Bengio. Everyone who is in machine learning should know about Yoshua Bengio. Yoshua Bengio, OCFRS FRCS, is a Canadian computer scientist and pioneer of artificial neural networks and deep learning. He is a professor at the University of Montreal and scientific director of the AI Institute. He has received the Turing Award and is one of the godfathers of AI along with Hinton and LeCun. Hinton has also received the Nobel Prize in 2024. In the paper, though, Bengio attributes the STE to Hinton. Another estimator of the expected gradient through stochastic neurons was proposed by Hinton in his lecture. The idea is to backpropagate through the hard threshold function as if it had been the identity function. It is clearly a biased estimator, but when considering a single layer of neutrons, it has the right sign. We call this the straight through estimator. A possible variant investigated here multiplies the gradient by the derivative of the sigmoid. So this is the diagram of the overall straight through estimator. Let's suppose we want to binarize the activations of a layer using the following function. The function will return 1 for every value that is greater than 0, otherwise it will return 0. This is similar to the quantization operation since you are reducing the precision of the output activations. As mentioned earlier, the gradient of this function is 0. To overcome this issue, a straight through estimator can be used in the backward pass. A straight through approximator basically it estimates the gradients of a function. It ignores the derivative of the threshold function and passes on the incoming gradient as if the function is an identity function. If going through the code seems intuitive to you, here is the code for it. So in the forward you just give if input greater than 0. You just check if input is greater than 0 and then so this will return 1 or 0 if it is negative, and in the backward you just do a hard 10H of the gradient output. Current popular methods in quantization aware training is QLoRA, where we fine tune the performance of LLMs to bring up the loss in accuracy. So this is the paper related to that. I have talked about efficiency of transformers using QLoRA in this video. Check it out. In that video we mainly talked about the code related to that and how to fine tune. Since this video is about how we are trying to achieve quantization, let's go over the theory of QLoRA a bit. So this is the diagram of QLoRA where they are showing the differences between full fine tuning LoRa and QLoRA. QLoRA improves over LoRa by quantizing the transformer model to 4-bit precision and using paged optimizers to handle memory spikes. The steps for the algorithm are: the weights of pre-trained neural networks are assumed to follow a zero-centered normal distribution, meaning they are distributed around a central value of 0. The weights are normalized in the range of -1 to 1. This normalization is achieved by dividing each weight by the Abs-Max algorithm, which we have discussed before. By normalizing the input data, we are distributing the weights around 0, and the less bits are required to store the exponential data of tensor or weight parameters. The exact values of NF4 are mentioned in the paper. Blockwise quantization divides input tensors into smaller blocks and quantizes each block independently, which reduces the problems of outliers. In this process, we split the input tensor into chunks, and each chunk is quantized independently, with each having their own quantization constant, that is total bins of data type divided by Abs-Max tensor. Even with outliers, We get much higher quantization precision and stability with block-wise k-bit quantization by confining outliers to blocks. So they flatten the weights and do the Absmax normalization after dividing into equal size blocks. You take each block and divide to 16 bins and then map to the closest NF4 value. Next is double quantization. Double quantization is the process of quantizing the quantization constants themselves for additional memory savings. QLoRA quantizes weights in blocks of 64, and while this facilitates precise 4-bit quantization, you also have to account for the scaling factors of each block, which increases the amount of memory required. Double quantization addresses this issue by performing a second round of quantization on the scaling factors for each block. The 32-bit scaling factors are compiled into blocks of 256 and quantized to 8-bit. Consequently, whereas 32-bit scaling factor for each block of previously added 0.5 bits per weight, double quantization brings this down to 0.127 bits. If you argue that is this really required, doesn't it seem insignificant? Then actually, when combined in a 65 billion LLM, this saves around 3 GB of memory. However, while NF4 is used to store quantized weights, QLoRA uses an additional data type, BFloat 16, which was also specifically designed for machine learning purposes to carry out calculations during forward and backward propagation. The storage part is also interesting and worth mentioning. This part depends on the library and is not actually mentioned in the paper. It turns out that the authors of Bits and Bytes, which is the official implementation of QLoRA, converts the 4-bit values into 8-bit by packing two 4-bit values into a single 8-bit value. This, of course, is in a different shape of the quantized tensor. This is because PyTorch does not support 4-bit data types, and the smallest type it supports is 8 bits. The reason it uses an 8-bit integer format and not an 8-bit floating point FP8 is due to lack of native support for FP8 in PyTorch. The packing operation is exactly what PyTorch new data type, quantized 4-bit integers, torch.quint4 into 2 does as well. You can see in the documentation. If going through the code makes more sense for you, here's the code for this. So you start with the NF4 quant levels. You specify the NF4 quant levels. Here is the binary representation of the uint4 values for the same NF4 quant levels as well, using 4-bit binaries instead of decimals for illustration purposes. Taking the weight tensor in the blocks, then you flatten them out. Then you normalize the tensor using the Absmax to fit within -1 to 1. Map each input to its nearest quantization level, then to its 4-bit binary representation. So you did do this here. Then once you do that, you get the packing, and that way you can pack two values into the same result, 8-bit result, setting it as torch uint8. So these are the 8-bit values. Another feature that they use to make inference faster is paged optimizers. So this is a feature provided by NVIDIA, which does automatic page-to-page transfers between CPU and GPU for error-free GPU processing in the scenario where GPU occasionally runs out of memory. This feature works like regular memory paging between CPU RAM and the disk. So basically, this is not exactly related to quantization, but the point being that in the papers they will try to use the latest features from the hardware as well to make things faster. So it's not only about the algorithm. Before we close this part 1 of the deep dive on quantization, I would like to go through this nice guide on how to perform quantization. To effectively quantize a model to int8, the steps are as follows. So choose which operators to quantize. Good operators to quantize are the one dominating it in terms of quantization computation time. For instance, linear projections and matrix multiplications. Try post training dynamic quantization. If is it fast enough? If it is fast enough, then stop there and then and use the dynamic quantization. Or if it is not fast enough, try post training static quantization. Basically point is that you check whatever speed you need and then you try to do more and more advanced quantization till you find the speed and the performance. So try post training quantization, which can be faster than dynamic quantization but often with a drop in accuracy. Apply observers to your models in places where you want to quantize, implies defining which quantization scheme to use. Perform calibration, convert the model to its quantized form. Are you getting good enough accuracy? Then use static quantization. Otherwise start quantization aware training this time. So this has been the overall view of quantization and a deep dive on it. If you have liked it, please like and subscribe. Stay tuned for the next part of this video where we will talk about different libraries.